The first mode of heat transfer that we'll be talking about is conduction. Consider an example like this. Uh, suppose there is some object. Okay, let's say a small rod or stick like this. Fine. Assume it is at room temperature. The entire rod is at the same temperature, that is room temperature. You can ignore that arrow, it doesn't make any sense here. Fine. Now, what will happen? Now, right now, the entire rod is at the same temperature. Okay. One of you tell me what will happen if we start heating one end of the rod. Let's say there is a candle or a burner placed here and you start heating one end of the rod. What will happen to the rod? The entire rod was initially at room temperature. You are holding it at one end, you are heating it at the other end. What will you observe? It will be better if you can unmute and tell. Okay, I got one answer as the end will get heated first. Okay, so the other end will get heated first. Heated, by heated he means temperature rises. Okay, then the heat will be transferred. Okay, okay. So one answer I got is that the temperature rises on this side, and so it will go to a temperature greater than room temperature. So basically there will be a temperature difference developed. Okay, between one end and the other end. And because there's a temperature difference, heat will get transferred. Okay. I I'm sure you all must have experienced this in real life also. If you hold it for sufficiently long enough, you can feel the heat in your hand also. You can feel the temperature rise in your fingers. Okay, at your fingers. So basically what is happening is heat is getting transferred from here to here. Okay, you need to allow some time for that to happen, but heat does get transferred from one end to the other. Okay. This is basically what we call as conduction. Transfer of heat through a medium from one place to another place. Okay. Now, let's consider two molecules of this system. Let's call this molecule as A and one molecule close to the fingers, let's call it as B. Now, the flame is near A. Okay. So A's temperature rises because the flame supplies heat to it. That makes sense. How does B's temperature rise? Is the molecule A, okay, I want all of you to answer this. Is the molecule A actually carrying heat from here to here? Is it going from one end of the rod to the other? Is the molecule A moving from one end to the other end after it gets heated? No. Okay. So there is no bulk movement of molecules. That does not happen. There is no bulk movement or net movement of molecules. Now we can't say molecules are at rest. Okay. At any temperature more than 0 Kelvin, molecular vibrations will keep happening. So molecules will be moving, but they'll be moving about their mean position. Okay. On average, they'll have a certain position, fixed position. So no bulk movement or net movement of molecules takes place here. And we know that. Okay. The object is a solid. How can a molecule simply go off to that side? Okay. In liquids and gases, maybe possible. It is possible, but in solids, that is not possible anyway. Then how is heat getting transferred? Any idea? Anyone think about it? Okay, I didn't get any answer so far. Can one of you recollect and tell me basically what is temperature a measure of? Vanilla
Heat
what?
supplied per molecule.
Okay. Don't say heat supplied per molecule. It's the energy per molecule. Okay. Whether you supply it, remove it, that is a different thing. How much energy is there per molecule? Temperature is a measure of that. Okay. Not exactly equal to the energy, but it depends on that. Okay. So higher temperatures mean higher amount of molecular vibrations. Okay. Lower temperatures, lower amount of molecular vibrations. Now we are increasing the temperature at one end by supplying heat. To the molecule A, if you supply heat, basically its temperature rises means it will be vibrating with a greater amplitude. It needs more space around it. Okay. And in that process, okay, basically when A tries to increase its molecular vibrations, it will push the molecule next to it. Or you can imagine them as layers. One layer of molecules, when it wants to vibrate with a greater amplitude, will have to push the next layer. Okay. Now, when one layer pushes the next layer will get disturbed. Means the next layer's temperature will change. That second layer will push the third layer. Third layer's temperature will change. Third layer will disturb the fourth layer. Fourth layer's temperature will change. So you can explain this transfer of heat in terms of vibration of layers of molecules. Fine. Whichever layer is first receiving the heat, that layer's amplitude of vibration will tend to increase. Then that layer will disturb the layer next to it. Disturbing means what? Transferring energy. Heat is getting transferred. Okay. That second layer transfers energy to the third layer and so on. That is what is conduction. Okay. Transfer of heat or transfer of energy from one layer of molecules to the layer next to it and so on. So that way, layer by layer, heat passes. And that passing of heat can happen only if there is a temperature difference between one layer and the next layer. Fine. That is what we call as conduction. So conduction requires a medium. Okay. Conduction of heat requires a medium. I mean, by definition, it is the transfer of heat from one layer of molecules to the next layer. So molecule should be there, means medium must be present, means it cannot happen in vacuum. Fine. Okay. Now, what we are going to discuss is how to find out how much heat gets transferred through conduction. See, conduction requires temperature difference between one point of the medium and another point of the medium. Temperature difference is there, should be there, only then heat gets transferred. What other factors it depends on, let us discuss. Uh, Imagine this. Suppose you are, okay, suppose there is a hot cup of tea. Okay, tea, water, milk, whatever it is that you prefer. Okay. Okay, let's assume you have been served a hot cup of tea. Now, before drinking it, you would like to check how hot it is, whether it is safe to drink or not. Now, you can do that by touching the cup of tea. Okay, touching the cup from outside. So, tell me, if you want to check how hot it is, how do you do it? Do you put one of your fingers, or like, do you try to maintain minimum contact with the cup, or do you grab it with both palms like this completely and then check how hot it is? What do you do? Do you try to maintain minimum contact or maximum contact to check how hot it is? Or if there are any other innovative ways that you can think of to estimate the temperature, you can tell me, you can share that also, not an issue. I am asking you to imagine this situation, touching it and estimating the temperature, just to get an idea of how hot it is. If there are any other ways you would use also, you can tell. Okay, I got one answer as we maintain minimum contact with the glass if we just want to check how hot it is. Okay, usually that is what we do. Uh, Even while taking bath, suppose there is a bucket of hot water and you just want to check how hot it is, then you don't directly pour it on yourself to check. No, you first touch it. Okay. So basically, what's the difference between pouring water on yourself and just touching it with your finger? Ensuring minimum contact. Why? What difference does it make if you hold it with both your palms compared to just touching it? Why do we try to maintain minimum contact? Like naturally, we all have this tendency. Why? Actual answer is safety. Okay. Suppose it is too hot, then if you maintain minimum contact, only some part of you will get hurt. Okay. A few molecules of your finger, okay, or a few cells of your finger will get hurt. If you maintain more contact, more cells of your body are going to get hurt. Why would you want to do that? Okay. So let us talk about the physics involved here. Basically, the heat is going to get transferred from the cup to your body. Okay. Through the finger or your entire palm, whichever way you prefer it. When you touch it, heat is going to get transferred. Okay. So basically, conduction is going to happen. It's not like the tea is going to fall on your hand. No, through the glass, it is going to pass. The heat is going to pass to your fingers. So conduction is happening. Transfer of heat through glass to your finger. From the tea to your fingers, heat is getting transferred through glass. Okay. So that heat transfer through conduction will happen. Fine. Now, what is the difference between touching with just one finger and touching with your entire palm? If you just touch with one finger, no, you are providing only few channels for heat transfer. Okay, you are providing a narrow path for heat transfer when you touch it with one finger. Okay, so suppose you bring it in contact with something else like this, right? There are only few molecules which can receive heat. Suppose you bring it in contact with something like this, then there are more channels for heat transfer. More heat will get transferred. Okay. So the amount of heat transferred through conduction is proportional to area of contact. Okay. Or we can better state it as it is proportional to cross-sectional area through which heat passes. Let's call it as A. Okay. If you just touch it with the tip of your finger, only a small cross section will be receiving heat. Okay. If you touch it with your entire palm, a large cross section will be receiving heat. And then definitely more heat will get transferred. So the amount of heat transferred is proportional to the area of cross section through which the heat can pass. Okay. So this is one thing we can tell about conduction. Another thing we can tell is that the amount of heat that gets transferred is proportional to the temperature difference, obviously. Okay, if there is very little temperature difference, even if you maintain contact for a lot of time, only a small amount of heat will get transferred. If there is a large temperature difference, more heat will get transferred, okay, in the same amount of time. So it's proportional to temperature difference. And obviously, it is proportional to the time that you allow also. Okay, this also we can experience from we can tell from everyday experience. You touch something hot just for a moment, some amount of heat will get transferred. You may feel hurt a little bit, but if you touch it longer, you will feel more hurt because more heat is getting transferred to your cells, okay, to the cells in your fingers. So more damage will happen. Okay, you'll get more hurt. So the amount of heat transferred is proportional to the time that you allow for heat transfer also. Okay. Now, suppose there is something very hot, but you have to hold it. Okay. Now you all think and tell me. Fine. Let's say there is a hot glass of water itself, water, milk, tea, whatever it is. You somehow have to hold it and take it from one place to another. Do you prefer holding it directly with your hand, or do you prefer wrapping a cloth around it and holding it? Is it safer to hold something hot directly, or is it safer to hold it by wrapping a cloth around it? Provided you maintain sufficient grip. Okay, wrapping a cloth around it is the safer option. Why? How does wrapping a cloth around it help? Okay, see, even when you wrap a cloth, heat will get transferred to your hand. Okay, I got one answer as Vijay Kalyan is saying it takes time for transfer of heat. Good, good. That is a good answer. Next answer I got is heat from the hot object gets transferred to the cloth first. Okay. Yeah, it has to pass through the cloth as well. So basically what you are doing is by wrapping it with cloth and then holding it, you are increasing the distance by which heat has to get transferred. Heat has to pass through the glass and then it has to pass through cloth also. Okay. Now again, from everyday experience, we can say that in a given amount of time, greater the distance by which heat has to pass, lesser the amount of heat that passes. Okay. So you can say in a certain amount of time, the heat transferred is inversely proportional to the distance by which the heat has to travel. Fine. Now, see, there are a lot of exceptions possible. It's not necessary that it is exactly inversely proportional. It can be proportional to 1 by L square. It can be proportional to 1 by square root of L. Many possibilities are there. In your syllabus, this is what we assume. Okay, this is the case that we consider. So in a given amount of time, if the distance by which heat has to travel is small, then you will see more amount of heat transfer happening. If the distance is large, then you will see less amount of heat transfer happening. So it is inversely proportional. Okay. And definitely the amount of heat transferred in a given amount of time for a given temperature difference for a given length depends on the material as well. Okay. Now you may have seen cups made of different materials. Some cups, even if you put hot liquid in them, from outside they feel normal only, or they don't feel that hot because they are made of materials which don't allow quick transfer of heat. On the other hand, some cups like steel or glass, they allow very quick transfer of heat, especially metals. Metals allow very quick transfer of heat. Okay. Wood, some kinds of fiber, they allow slower transfer of heat. So, how quickly heat gets transferred, or in a given amount of time, how much heat gets transferred depends on the material as well. Okay. So, putting all these factors together in one formula, the heat transferred is proportional to area of cross section, which is available for heat to get transferred. It's proportional to temperature difference. Now, see, we are using the symbol delta here, but don't mistake it for change in temperature. Here you should read this as difference in temperature. Change in temperature is for one object. Okay, let's say one molecule initially is at a temperature 20 degrees. If it rises to 30 degrees, then the change is 10. It's the same molecule's temperature. Okay. But here we are talking about conduction, heat transfer from one point to another. The delta T here is the temperature difference between this point and that other point. Okay, so don't read this as change in temperature, read this as difference in temperature. Okay, it depends on the time that you allow for heat transfer. It is inversely proportional to the distance for heat transfer. So putting all these together, you get delta Q proportional to A delta T small t or delta small t. Delta capital T is temperature difference. Delta small t is the time that you allow. Okay. So capital T is for temperature, small t is for time, and inversely proportional to length. Okay. And the proportionality constant depends on the material through which the heat is passing. And we call it as thermal conductivity of that material, denoted by the symbol small k. So delta Q can be written as Ka delta capital T delta small t divided by L. Now send the delta small t to this side. You can write delta Q divided by delta T. That is heat transferred per unit time. So basically it tells you how quickly heat is getting transferred. That can be expressed as Ka delta capital T divided by L. So this is what we call as rate of transfer of heat through conduction. Fine. You can write it as dq by dt also. So usually we write it as delta q by delta t, but there are some conditions which need to be satisfied before you apply this. Now, when you write an equation like this, indirectly you are assuming that the entire material has the same conductivity. Okay, so these are the assumptions. K, conductivity must be uniform. Next, you are also assuming that the area of cross section through which heat is passing is always the same. Area of cross section must be uniform. If it is non-uniform, you cannot use this equation. Okay. So if there is a rod or a wire whose area of cross section changes from layer to layer, then you can't use this equation. Okay. I know, like you will already have gotten the thought also. In those cases, you may have to integrate. Okay. So this is a simple form of the equation which gives you the rate of heat transfer through conduction. So if you know the temperature difference across the conductor, conductor means any medium which is allowing heat transfer, you call it as a conductor. If you know the temperature difference, area of cross section, length and conductivity, you can tell how quickly heat is going to get transferred. And if you know the time, you can even tell how much heat gets transferred. Fine. Okay. First of all, derive the SI unit and dimensional formula of thermal conductivity. Do it all of you quickly. SI unit and dimensional formula of thermal conductivity K. Okay. Uh, Heat will be in joules. Time is in seconds. Area meter square. Length is in meters, so one of them can be cancelled. Temperature difference you can write in Celsius degrees or Kelvin SI unit. Okay. So joule per second. Joule per second. Energy per unit time is nothing but power. Okay. Watts. So joule per second can be written as watts. And you send the remaining units that side. So watts per meter per Kelvin. Okay, that is the SI unit. You can also write it as watts per meter per Celsius degree because difference in temperature also will be in same whether you write it in Celsius units or in Kelvin units. Okay, so watt per meter per Kelvin, dimensional formula you can derive. Not a big deal. Fine. So basically that is what is conduction, transfer of heat from one layer to the next and so on. So conduction requires a medium and the rate at which heat gets transferred through conduction depends on certain factors as we discussed. Delta Q by delta T is equal to delta Q by delta small t. Okay, that is heat transferred per unit time is equal to Ka delta capital T divided by L. Okay. So this delta Q by delta T that is there, you can also write it as dq by dt and we call it as heat current. Okay, rate of transfer of heat, we call it as heat current. Fine. Basically, heat is flowing. No, if anything is flowing, you call it as a current of that thing. Okay. So dq by dt becomes heat current, and that is given by Ka delta capital T divided by L. But remember the conditions. This is valid only when conductivity K is uniform throughout the conductor. Area of cross section has to be same everywhere. Then you can use this. Okay. Lot of variations are possible. So problems based on this formula we will be solving in tomorrow's class. Okay. Thank you all. We'll continue tomorrow.